The recording I remembered today. Kinematics is basically when we study position, an object's position, an object's velocity, and an object's acceleration, right? So when we are talking about these things, in particular when we're relating them to concepts in calculus, what we're really studying is kinematics. Now, we're going to go over some basic concepts that you should know, as well as some things that are new to you. So the first thing that it talks about here with this, a very quick physics lesson, is that a position function, little s of t, describes an object's position at any given time. The first thing that you need to note is that sometimes you see a capital S of t, and that often stands for speed. Whereas if you have lowercase s sub t, that stands for position. Well, every object has an origin, a reference point, right? We call that reference point an origin. So in the same manner that, I'm gonna lower this, in the same manner that on our xy axis we have an origin as 0, 0, an object also has a reference point or origin, right? Now, with regard to a particular time, an object's position may be greater than 0, which means it's to the right of that origin. At a particular time, an object's position may be less than 0, which means it's to the left of its origin. Or at a particular time, an object may be positioned on its origin. So this is just in relation to an object's position. Where is your object? Is it to the right of the origin, to the left of the origin, or is it on the origin point? Questions so far? Okay, when the object changes its position, this is called velocity. Now, one thing that we need to specify the difference of, which I hope you know, is the difference between speed and velocity. Okay, what is the difference between speed and velocity?
Speed is like how fast, velocity is how it changes.
So kind of, right? If we talk about speed, we can say 25 meters per second, right? That's speed. In fact, we say that speed is the magnitude of velocity. What is a magnitude? What's the magnitude of an earthquake? The size of the earthquake, right? When we talk about magnitude in relation to speed, position, and acceleration, we're talking about distance. How far? That's what we mean by size. How far are you? If we're talking about speed being 25 meters per second, how far is it going? 25 meters every second. So speed is the magnitude of a velocity. Velocity has one added component that speed does not have. Can anyone tell me what that is? Yeah.
Is it at a given direction?
Direction. Right. So speed is 25 meters per second. velocity is 25 meters per second to the east, right? So, this has, velocity has direction. Has direction. And magnitude. So it tells me how far I'm going every second, 25 meters every second, and in what direction I'm going that 25 meters per second. I'm going north, south, east, west, right? Whereas speed has just direction. I'm going to use a different color. Now, you may have heard the term scalar and vector before, have you? Which one's a scalar and which one's a vector? Yeah, velocity is the vector because it has direction, right? And speed is a scalar because it just has direction without, or it just has magnitude. Sorry, I need to change that to magnitude. It just has magnitude. And so this is my vector, and this is my scalar. Make that a little bit more legible. Scalar. All right. Questions so far? No? Okay. So sometimes we are able to model an object's position, and from that position equation, we can actually use calculus to find the equation for our velocity, our instantaneous velocity, our velocity at a given time, and we can derive that velocity equation to find our acceleration. So as you can see here, velocity is the derivative of the position function, right? So I'm given a position function, I take the derivative, that rate of change. The rate of change of your position function is velocity, right? Likewise, the rate of change of your velocity is your acceleration. With me so far? So if we have one, we can find the other. In fact, next year when we learn about integration, we'll be able to go backwards. Right now we can only go forwards. We can find the derivative, right? Okay. So just to reiterate, it says when the object changes position, this is called its velocity. How fast an object is changing its position is called acceleration. So acceleration is just how is your velocity changing? Right? How fast is it changing? Okay, so let's evaluate some signs of velocity and acceleration and see what's going on. So basically, anytime you have a positive velocity, if we go back to that 25 meters per second, since velocity is a vector quantity, it'll tell you direction, right? So if it's positive, that means that you're moving to the right. So it could be 25 meters per second to the right, right? So moving right. Likewise, if you have a negative velocity, that just means that you're moving to the left at a given speed. And then if you are dealing with a velocity of 0, that means you're at rest. You're not moving left or right. Yeah. So at rest. So because we see how fast, it says how fast it is changing its position is called the acceleration. If we have a positive acceleration, what does that mean? The what? Yeah, its velocity is increasing, right? We have an increased velocity, so velocity is increasing. So maybe we're going to the right 25 meters per second, and then we're going to the right 30 meters per second, and then we're going to the right 35 meters per second, and then 40 meters per second. It's accelerating, right? Your velocity is increasing over time. That's what acceleration is. It says that your velocity is increasing. Or it says when that value is negative, that your velocity is decreasing. Now, what does it mean, do you think, when your acceleration is 0?
Velocity's not changing.
Yeah. Yeah, so the velocity is not changing, right? So, velocity is constant. That's what we say when it's not changing, right? Or it's reached its maximum velocity or minimum velocity, right? So, or max slash minimum velocity. Because once it's reached that lower crest or upper crest, it can't go any higher or any lower, right? So that also can tell us if it's a maximum or minimum, and we really have to do a sign diagram to determine if it's going to be max or min. What questions do we have so far on these concepts of position, speed, velocity, and the signs of velocity and acceleration? Now, you have to remember that there is a difference between velocity and speed. Speed is not as detailed as velocity because it doesn't have that extra component, that component being the direction, as Akil said. Okay. Make sure I covered everything here. In which your velocity is being 0. We talked about that here with this chart. So here's just another visual that solidifies that concept that I just talked about. Your speed of your car being 25 meters per second, and your velocity being negative 25 meters per second. That negative tells me it's moving left. So just by having the sign there, I know a direction. Likewise, the same thing here. 25 meters per second doesn't tell me a direction, but if I put a plus sign in front of it, that tells me the direction is to the right. Okay, now your book has a useful chart that I want to elaborate on about when things are set equal to 0. Some of them are pretty easy to understand and some of them are a little bit more tricky. So first of all, let's label this chart. Your T is your time, of course. Then you've got your position. Remember, little s does not mean speed, it means position. Then you've got your velocity. And you've got your acceleration. So in questions that involve kinematics, you can see these phrases that involve the words initial conditions, at the origin, when something is stationary, when an object is reverses, when an object has maximum or minimum displacement, when it has constant velocity, or when it has maximum or minimum velocity. So like that list that I created about the first and second derivative tests and you referred back to, this is a good chart to refer to when you're doing these kinematic problems. And the more you do them, the more used to you will get to this chart. So initial conditions means what's happening before we even do anything, right? Before time passes. We're used to that, right? And in many problems, we see the words initial, right? So that's when time is equal to 0. At the origin, we already know from the page before, the previous notes, that that's when your position is equal to 0. It is on the origin point. If it's greater than 0, it's to the right of the origin, less than 0 to the left of the origin, right? Stationary. Stationary is when an object is at rest, right? So that's when your velocity is 0. And then you have when your object reverses. So this is a little bit tricky to understand here. So we understand that when we're stationary, our velocity is 0, right? But why is it that when we talk about an object reversing, why is the velocity 0? Any thoughts?
No idea.
No idea. Okay, I thought that would happen. So, here, when it talks about maximum or minimum displacement, your velocity also being 0, so now, Flora alluded to this constant velocity earlier with your acceleration being 0. Well, acceleration has to do with whether or not you are speeding up or slowing down, right? And speeding up with direction is, of course, velocity. So if you're not speeding up or slowing down and your velocity is constant, then your acceleration is 0, right? And the same thing is true with that maximum or minimum velocity. The acceleration is 0. Questions? All right, so let's just practice. Let's practice some problems. So this one's actually from your book. It's a little bit challenging. It gives you a situation with a particle. It says a particle moves. Let me zoom in. It says a particle moves given by the function. So it's modeling the position, s of t equals t cubed minus 3t plus 1 centimeters, where t is time in seconds and t is greater than or equal to 0, obviously, because we don't want to go backwards in time, because we can't. So it says find the position's velocity and acceleration functions and draw a sign diagram for each. Find the initial conditions. So you see that word initial conditions, go back to the chart. What does that mean? And who's described the motion at that instant? Describe the motion of the particle at 2 seconds. Find the position of the particle when the changes in direction occur. So when it's going left and then changes to right or vice versa. For what time interval is the particle speed increasing? And then what is the total distance traveled by the particle from 0 seconds to 2 seconds? Okay, so I'm going to work on this with you step by step, and then you're going to try the next one completely on your own and we'll check. Okay? So, what is the first one asking me to do? How do I find the equation for velocity? Don't all say it at once. Well, using calculus.
So we find the
Derivative, right. The first derivative of the position is velocity. And then the second derivative is acceleration. So we're going to find those equations for velocity and acceleration. So A, what is the derivative of my position function? Yeah, So my velocity at a certain time is 3t squared minus 3. So that's the equation that will tell me the velocity at a given time, the instantaneous velocity. What about acceleration? What's that? Yeah. $6t. Okay, it says draw a sign diagram for each. When it says that, just draw a sign diagram for each, it wants you to use those critical values. How do I find critical values again? Akil, do you remember? What's a critical value? Critical points meaning where you possibly have maximums or minimums, right? And when we're finding those critical values, it involves us setting the derivative equal to what? 0. So we have to set our velocity equal to 0 and solve for t, and set our acceleration equal to 0 and solve for t. So let's go ahead and do that now. So what did we get for t for our velocity function set equal to 0? One. What about our acceleration? We get 0, right? So let's go ahead and draw sign diagrams for our velocity function. And let's draw a sign diagram for our acceleration function. And this represents our time. Okay. For our velocity function, when I am to the right of 1, what's my sign? Is it positive or negative? Positive. When I'm to the left of 1, what is my sign?
There shouldn't be a, like, it crosses at -1.
It crosses at, well, no, -1. When I'm talking about -1, we're talking about time, and time cannot be negative. So I can't include that on the sign diagram here because there is a particular restraint on time.
So it's gonna be negative.
Yeah, because even look at the domain. T is greater than or equal to 0. So we can't include -1. Yeah, yep. The domain already tells us that time has to be greater than or equal to 0 too.
How do we figure out the direction?
Right. So
Oh, yeah, that.
here, your object is at rest, right? And then here, what direction are you moving in? And what direction are you moving here? Left. So let's think about our sign for our acceleration now. So that's how you determine the direction. Bigger than 1 is to the right, smaller than 1 is to the left. Now on our acceleration sign diagram, we can't go to the left of 0, so what's the sign to the right of 0? Positive, right? So what's happening here when we have a positive velocity and a positive acceleration? You're increasing velocity, right? So when your velocity and acceleration have the same sign, it's increasing its velocity. The object is getting faster and faster and faster. Does that make sense? Now, if they're both negative, that's okay too. It just means that it's going the opposite direction, but still getting faster and faster and faster in the opposite direction. But if your velocity and acceleration have opposite signs, that's when you're slowing down. Does that make sense? Okay. So when velocity and acceleration have same signs, the velocity increases. And then when they have different signs, the velocity decreases. Is it possible what? That both velocity and acceleration increases. Well, acceleration is just telling you if your velocity is increasing or decreasing. You can have a constant acceleration if, let's say, you have a squared function and then your derivative of your squared function is something to the first, and then your derivative of something to the first is just a constant. That would mean that your acceleration is increasing at a constant rate or decreasing at a constant rate, right? But in this case, when our signs are the same, it just means, okay, your object has a particular velocity, 25 meters per second, and it's moving to the right, your object is. And if we also have a positive acceleration, well, that means that as your object is moving to the right, it's increasing in its velocity every single time, not necessarily by a constant amount. If it were negative, then you're saying, okay, well, my object is moving left and at a certain 25 meters per second, and my acceleration is also negative, which means in the direction left, my object is speeding up because they share the same sign. It's when they're opposite signs, when you have an object moving to the left at a certain meters per second, and then you have an acceleration being positive, that you end up slowing your objects down. It's a little bit conceptual thinking with the signs. Is that okay? Okay. This actually will help us walk through that. So we did the sign diagrams, find the initial conditions, and hence describe the motion at this instant. Initial conditions meaning time is what? 0, right? So let's go ahead and plug in our time of 0 for our position function, our velocity function, and our acceleration function and see what this means. So for B, I'm going to find S sub 0, V, not sub, S of 0, V of 0, and A of 0. What's the position of your object initially? One what? 1 meter, but is it? It's 1 meter, right? Because it's position, but is it 1 meter from what? From the origin, right? Because if it were 0, if S of 0 equals 0, that means it's on the reference point, it's on the origin. But if we get a positive number, which we do, this means the object is 1 meter from O, our origin. Oh, 1 centimeter. Thank you. Okay, cool. If we get V of 0, what does that give us? -3. -3, okay, centimeters per second, right? actually, in the IB, instead of centimeters per second, they just do centimeters second to the -1, right? Because if you do a negative exponent, you bring it to the denominator. So instead of putting centimeters over seconds, they typically write centimeters and seconds all in the same line and then just put it to the -1. Okay, what does that mean? Your object starts at 1 centimeter to the right of the origin, right? Why to the right? Because it's positive. -3 centimeters per second means what? Your object, your particle, is doing what? Moving in what direction? Yes, it's moving left 3 centimeters per second. So it starts off 1 centimeter from wherever its reference point is, and then it moves left 3 centimeters per second. Okay, so object moves left 3 centimeters per second. Okay. And then your acceleration, you get 0. And since it's the second derivative, it's to the -2. 0 centimeters per second squared. What does that mean? Yeah. It's moving left, and when it's moving left, it's staying at 3 centimeters per second. It's not going from 3 centimeters per second to 4 centimeters per second to 5 centimeters per second. It's just staying 3 centimeters per second. Okay. So the velocity is constant. Okay. Questions so far? Let's do C. C says, now tell me what happens at 2 seconds to the object. So likewise, you find S of 2, V of 2, and A of 2. What is S of 2? 3. Which means what in the context of this problem? What does that mean? Your object is where? To the right of the origin, right? 3 centimeters to the right of the origin. Your velocity is what? 9 centimeters per second, which means what? Yeah, so it means that it's moving to the right at 9 centimeters per second. And your acceleration is 12 centimeters per second squared. What does that mean? Yeah, your velocity is increasing at a rate of 12 centimeters per second, right? Questions so far? All right, so let's actually think about what's happening to our object overall. But first, let's answer question D. Find the position of the particle when the changes in direction occur. Okay. Where is it changing direct? First of all, what does direction have to do with? Position, velocity, or acceleration? Position tells you to the right of the origin, to the left of the origin, but also velocity, right? So when can I determine when something changes direction? When would it be here? Yes. When its velocity changes signs, right? Because it's traveling to the right, it's traveling to the left. So, for what time, so it says find the position of the particle when the changes in direction occur. So what time are we gonna plug in to find the change in direction? At time 1. Because even though the object is at rest, the velocity is gonna give you 0 when you plug in 1. The particle to the right of 1 and to the left of 1, that's when it changes direction. So if I plug in 1, not for velocity, but for my position function, I get the position of the particle when the changes in direction occur. Where is this object at 1 second? Does that make sense? Because there's a change in sign here, which means it changes direction. It is at rest instantaneously at 1, but to the right of 1 and to the left of 1, it has different signs, which means a change in direction occurs. Does that make sense? So let's find S of 1, find the position of the particle. Okay. So let's go ahead and find S of 1. Because exactly what Flora said. You're changing signs to the right and to the left of that instantaneous time. So what do I get for my position? Well, I get 1 cubed minus 3 plus 1, which is equal to -1, which means when does it change direction? Akil, when does it change direction? If I get -1 for the position at which it changes direction, what does that mean? Oh, -1, what does that mean? What does -1 mean in reference to the origin?
1 centimeter to the left.
Yeah, exactly. Right. So at 1 centimeter to the left of the origin, that's when it changes direction. Yeah. Because values to the right and to the left of this time are of opposite signs. So this is when, so it's going at a certain, I'm gonna actually draw the motion diagram for you to see what's going on. But because you have a difference in the signs to the right and to the left of this particular time, at this time, this is when a change in direction happens. It is going and then it goes in reverse at whatever this time is. So I'm going to show you a diagram. It'll help clarify it. Yes.
So instead of 1 and 2, you would input 2?
Yes, if your sign diagram, with your sign diagram, if it was 2 instead of 1, yeah, you would input 2. Okay, so I'm going to clarify Michelle's question because I see where she's a little bit lost here. So for D, 1 left of the origin, 1 centimeter left of your origin. Okay. Now let's draw a position diagram so you can see what's actually happening to our particle. So I'm going to draw. Okay, so this is the position. So instead of time, this is going to model the position of our particle. Our particle has an origin. Oh, I'm sorry. Okay. Our particle has an origin, right? And we're going to see what happens when it's 1 centimeter away, 2 centimeters away, etc., right? This is in centimeters. And then if it's to the left, 1 centimeter, or to the left, 2 centimeters. So where does our object begin? At 1. So here we are. Here's our object, right? 1 to the right. Yeah? And then what happens, right? What happens to our object? Does it start going to the left? Does it start going to the right? It goes left, right? How did you know it went left? Yeah, the velocity is negative, right? So it goes left. So it goes left. And then when it's 1 to the left of the origin, what happens? It changes direction. Why? Because the velocity, the sign diagram for velocity says negative on one side of 1, positive on the other side of 1. 1 is where your object is at rest. On either side of that, you have 2 different signs. So position-wise, not velocity-wise, but position-wise, when you're at 1 to the left of the origin, which is what we get when we plug in 1 per position, I am changing direction. Now I'm going that way. My particle starts here. I have negative velocity at time 1. Right now it's at rest and then it changes direction. It's at rest and then it changes direction. Does that make sense? Does that clarify it a little bit better?
Yeah, I get how it's not, but I don't understand why where you start has to be where it changes.
Because, like we said, velocity has to do with change in displacement. And change in displacement, so okay, so let me think about an easier way to explain this. So when you're changing signs in your velocity, you're going right, then you're going left, right? That's a change in direction. That's what velocity is. It's telling you not only the rate, how fast you're going, but the direction that you're going, right? So if at a certain time, my velocity is saying I'm 25 meters per second to the right, and then that's to the right of the time of 1. But then to the left of the time of 1, I'm now going left at 25 centimeters per second. So,
I give up.
you don't get it?
I just don't get why. No, because we plug in 1 for x.
For your time. That's when your object's at rest.
Yeah. 1 is the point where the object is at rest. And then I don't get why when we plug that into the function, it gets a point where it changes directions. Like, I don't know how. What did you say? Is 1 where is 1 both the object at rest and where it changes direction?
Yes. Because anything to the right and left of that has opposite signs.
So say if it's type 2, then it would change at negative.
If it were 2, it would change at negative 2.
Like if the point starts as 2 is.
If the point is at rest at after 2 seconds,
Say if the position of the object at rest is 2 centimeters right to the origin,
It depends on your sign diagram. If your sign diagram changes from negative to positive or positive to negative, if your velocity, for your velocity, the velocity sign diagram changes signs, you are automatically changing directions, right? At that particular time, your velocity is 0, right? But past that, you're going the opposite direction that you were going. Yeah, you're going, you stop, and then you go backwards. That's what's happening. Does that make sense? That's what it's saying. Is you're going, you stop, and then you go back. So that's when does it change direction? Wherever you are when you stopped. Because you stopped and then you went back. Does that make sense? Okay.
Yeah.
Okay. Boy, this is a long question. All right, where are we? E, for what time interval is the particle's speed increasing? Well, what does speed increasing, what signs am I looking for velocity and acceleration? Flora mentioned this earlier. Same sign. Same sign. Well, where are your velocity and acceleration the same sign? Here. Yeah, and actually, I actually got confused on this and I had to ask Ms. Chi, and Ms. Chi says it doesn't matter because your book says when t is greater than or equal to 1. And my question was, wait a minute, at 1 it's at rest. So how are you increasing speed? And I think it's the same idea, is that you're going along and at rest you have enough momentum to still increase your speed because you're still, from the point at which you're in rest, you're increasing your speed because you're going from 0 to 5 centimeters per second to 6 centimeters per second to 7 centimeters per second. That's why t is greater than or equal to 0. Or greater than 0. I know she says it doesn't matter. But the book says greater than or equal to 0. Does that make sense? Oh, I'm sorry, greater than or equal to 1. Yeah, greater than or equal to 1. So E is greater than or equal to 1. Okay, what is the total distance traveled by the particle in 2 seconds? From here to here, from here to here, from here to here, from here to here, and from here to here, right? How far is that? 1, 2, 3, 4, 5, and this is position, right? So at t equals 3, or at 2 seconds, you actually get 3. So it goes one more, you get 3 centimeters. So it travels a total of 6 centimeters. Does that make sense? This is your position. So if you plug in, this is not time. So if you plug in 2 seconds, you get a position of 3 centimeters. So in 2 seconds, from 0 to 2, you travel 6 total centimeters. Yeah? Because, well, the displacement is going to tell you the distance. The displacement takes into account the fact that you're going back. So you have to count, okay, I'm going, and then I'm going back, right? That's the displacement. You're moving left. So that's 1 unit back, 1 unit back, then 1 unit forward, so you change direction. Then another unit forward, then another unit forward, another unit forward. Because at time 2 seconds, you actually are at 3 centimeters. So you travel a total of 6 centimeters. All right. Are we okay? Or do you feel, to be honest, do you feel like you're getting some of this? No. Well, what can I do?
I need to go through the physics book.
What is it that we're not understanding? Because you're talking about it.
I don't know what I don't understand because you don't understand.
Okay, so here's the homework. Your homework, I was going to give you a worksheet, but I'll save that for tomorrow. If you can promise me one thing, go over this question again. It's in your book. Go over the other question I didn't get to in the notes. I'm gonna post a couple videos, watch those videos. And come back, we'll be ready to discuss a few more ID style test questions. Okay? That's your homework, and then tomorrow I'll give you the worksheet. Alright? So you promise me this, that you'll look over these? Okay, pinky promise, thanks.
These are my old exams.
Oh, thank you.
It stayed in my bag for forever, so
At
it's
least
so
I
good.
have them.
Yeah.
Thank
At
you.
least they're not like destroyed.
It's hard stuff, guys. It'll be fine. Physics. Yeah, with particles moving left and right.
Boy.
It's a tough one. Tough one.
What, yours?
Oh yeah, I was gonna give this homework out today, but we didn't get to it. I need to observe a colleague.
See you. See a nice picture.
Oh my.
Put a nail into my hand. With a power nailer.
What is it?
I put a nail into my hand with a power nailer. I was holding something, went bang.
Oh my, that looks like it hurt.
Yeah, it was, the second it happened, it didn't hurt. It was surprising. It wasn't until a little bit after it started throbbing.
Like, oh, there's a nail in my.
Yeah, that's right.